everybody. In section 6.3, we're going to look at a couple more approximation techniques for finding definite integrals that don't necessarily have antiderivatives that we can find using our technique so far, or even sometimes just in general. Like no one can find an antiderivative of some functions. So we're going to talk about two rules. One's called the Trapezoid Rule and one is called Simpson's Rule. So just to recap what we have so far, our integration toolbox, here are all of our techniques, and it's pretty much full for this semester. We're not going to learn any more techniques. We've got algebra, our basic antiderivatives, we've got U substitution, basic and total, we've got integration by parts, partial fraction decomposition, and integration tables. And then our approximation toolbox, we learned about the midpoint rule in the past, or Riemann sums, and then we just have these two rules in this section, trapezoid and Simpson's rule. So like I said, there are certain what are called non-elementary integrals for which there is just no antiderivative. So for example, the integral of e to the x squared. This function e to the x squared, there is no antiderivative of that. There's no function that has a derivative of e to the x squared. And you can just think about what you might try here, like with the tools that we have so far, and nothing works. And that's also the case, for example, for sine of x over x, for sine of x squared, for 1 over natural log of x, and many, many more. And these are pretty simple looking functions, so it's kind of weird that we just don't have any antiderivatives for things like this. So if the integral is definite, the best we can do is approximate it. And so far we have learned one technique, or the midpoint rule, which uses rectangles to approximate the area. We also looked at left sum, right sum, and averaging those as well. So in this section, we're going to learn two better ways of approximating definite integrals. And the first is called the trapezoid rule, because it uses trapezoids instead of rectangles to approximate the curve. So here's just a drawing over here of some function. So here's our f of x function that would be in our integral. And we're, just like with the midpoint rule, we're going to be integrating from some point A to some point B, and we're going to want to separate this out into an evenly spaced number of trapezoids, or divide this up into intervals of even length. Then what we do is we will, instead of, in the past we've kind of made, find our height and made this a rectangle here. But what we'll do instead is just connect these points together. And the shape that we get here when we make this upper piece sort of diagonal like this is a trapezoid. And we'll do this for every single interval here. And you can see with the function that I have, it's pretty close. Depending how curvy the function is, approximating it with a line is much better. Like a diagonal one here is much better than a horizontal one, like with rectangles. So the task is going to be I've got the formula here, and we'll just walk through where it comes from. I know it looks kind of crazy right now, but to start, we are going to want to find the area of, in this case, I've got just 4 trapezoids. So in general, the area of a trapezoid over here is so it's 1/2 times the base, which is the distance at the bottom, the way that I've drawn it, and then you add the 2 heights. So basically, this is a simplified version. If you were to put this in here, you average the heights of each side, and then you multiply that by the base. With our function notation and everything, if we just consider our first trapezoid over here, I've just rewritten this shape and this formula in our function notation. So the distance b here is going to be the width, or the length here between our x values, or that's what we were calling delta x. And this is the same thing that we found using that we were using our midpoint rule. So this is just the length of the whole interval divided by the number of trapezoids that we have, which in this case, my picture, I have 4 of them. So n here would be 4. But we'll have an actual number for that. And then the height on this side, right, that's just the function height at this x value, so at the left x value. And then over here, again, just for this specific trapezoid, the height, this length, is the function evaluated at this x value, at x1. And so if I just substitute these in and just translate, like b is delta x, the first height's f of x sub 0, and then the second height is f of x sub 1. And so when we add all of these up, right, here's the area of the first trapezoid. Here's the area of the second trapezoid. So this uses these 2 x values, right, x1, x2. This is the third trapezoid, x2, x3. And then here's the last trapezoid with x3 and x4. Then what we can do is notice that there is this in common everywhere in all of our 4 terms. And so we can then factor this out. So this 1/2 times delta x, this is kind of like the GCF overall of the whole thing. And then what we're left with in this set of parentheses here is basically just all of the function values added up. And what we see is that there are some ones that repeat, right? We end up having f of x sub 1 here twice. We have f of x sub 2 here also twice. We have f of x sub 3 here twice. And then the end ones, this one, the first one, the last one here, we only used them in the first trapezoid for x sub 0 and the last trapezoid for x sub 4. But every one in the middle got repeated because it's the right side of one trapezoid and the left side of the next trapezoid. So we can add these together and just put a 2f of x1, right? Same thing here. This is 2f of x2, and then here this is 2f of x3. And so this is our like nice sort of simplified-ish form for our trapezoid rule. Now we're gonna just generalize this to not just 4 trapezoids, but any number, like n trapezoids. So here is the sort of like actual summary and generally written for the trapezoid rule. So again, it's for approximating definite integrals, the integral from a to b of f of x, using n trapezoids. So just like we did like m sub n, we're going to just call this like t sub n. So in the previous example, that would have been like t4 because we had 4 of them. And then this is a little different than what I had written before in the previous slide, but here this is, so remember that delta x, what we had 1/2 delta x here. So delta x is b minus a over n. And so if I were to just sort of simplify everything into a nice, neat formula that we can just use, all we do is just like multiply fractions together, and this ends up being b minus a over 2n. Now in the midpoint rule, this 2 wasn't there, so this is like a key difference that we have to pay attention to. And then also the key difference is like we have these 2's right in front of basically every function value, every height here that's not the first one or the second one needs to be doubled. So I don't know how many there are, but I just have here like up until the second to last one gets a 2 in the front, and then this is the last one here that just has a 1. Right, so n is the number of trapezoids, x sub 0 is the starting point a, the last x, x sub n, is the ending point b, and then again the delta x is the b minus a over n, and it's the width of each trapezoid or the width of each subinterval. Okay, so this formula here, this is like one to like memorize to know what the formula is to use the trapezoid rule. So let's look at an example. I'll just do one example of this, and I encourage you to pause this video and see if you can just like work it out using the rule and the formula. Okay, so here we're going to look at just that one, the first integral that I told you, from 0 to 1 of e to the x squared. And we'll use this with n equals 4 trapezoids. So to start, we're going to need to find delta x, right? And just like before, that's b minus a over n. B is 1 and a is 0, and we've got n equals 4, so our delta x, the width, is 1 over 4. Okay, then we need all of our like x sub 0, x1, x2, x3, x4, so we're going to have to find all of those. These are just going to be, each one will be 1/4, 1/4 away from the previous one. So we start, x sub 0 is a, so it's going to be 0, and then our ending point is 1. And then we'll just go up by 1/4 each time. So 1/4, add 1/4 to that, that's 1/2, add 1/4 to that, that's 3/4, and then add 1/4 to that, and that gives you 1, which, just to double check, that does end where we want it to end. And then that's pretty much it. Then you just substitute into the formula. So this is going to be, in notation, this is t sub 4. And it's b minus a over 2n. So I'm going to do 1 minus 0 over 2 times 4. Or you can just take the delta x here and multiply it by 1/2 if you like. And then we're going to take, so it's f of x 0, so it's going to be e to the 0 squared. Then it's plus 2 times f of x 1, so 2e to the 1/4 squared. And then every one in the middle is going to get a 2, so 2e to the 1/2 squared plus 2e to the 3/4 squared. And then here's our last one that we won't have a 2 in the front of, so it'll be just 1e to the 1 squared. And if you calculate which of these things are, I would, if you have a graphing calculator, you can, I would just like kind of keep them all in there and add them all up with as many decimal places as you, as it can hold. But if you need to write it down in round, I would go out to like at least 4 or 5 decimal places, and then you'll add them all up, and we will then multiply by 1 over 8. So here's just what each of the values are sort of separately if you want to check your work for that. And if you add those all up and you multiply by 1/8 or divide by 8, you'll get about 1.4907. And so there's an approximation for that definite integral. So over here on the right is a graph of e to the x squared, and so just to, it's been a while since we talked about area maybe, but remember definite integrals, right, are approximations of the area under the curve. So here that area is approximately 1.4907. All right, so I don't think that, I'm not going to do another example of this. I encourage you to just try some on WebAssign, see how it goes, and if there are any issues, then we can talk about it in class or in office hours. The second rule in this section, there's just 2 things in this, is trapezoid rule, and then we have what's called Simpson's rule. Now, the proving of this rule is much more complicated than the trapezoid rule, but the idea of it is to use parabolas to estimate the curve on each subinterval. So that's kind of nice because instead of approximating parts of the curve with lines, we are going to approximate parts of the curve with a curve, which is even better. So this is like the best approximation technique that we will see together. So here is the formula for it, and we'll use S sub n just like we do with all the other ones. So just S for Simpson's rule, n is going to be the number of subintervals that we have. Now you'll notice some similarities here, like b minus a, and then we have an n here, but a key difference is that we have a 3 times in the bottom, whereas with the trapezoid rule we had a 2. We have some similar stuff here, like the n's, the f of the first x and the f of the last x do not have any numbers like multiplied here. There's just a 1 and a 1. But the middle ones here do have some numbers multiplied, and it alternates. So we have the first value, f of x value, that's after the very first one, so the second one, has a 4 in the front, and then this one after that has a 2 multiplied in the front. And then we go back to a 4 multiplied in the front, and so it goes like a 1 for the first one, and then it's 4, 2, 4, 2, 4, 2, and it keeps alternating. And then the very last one, before the last one, sorry, so the second to last one has ends on a 4. And then the very last one, again, just has no number multiplied. So the one before this one would be like 2. If we go 2 back, it would be a 2 in the front. Okay, so alternates 4, 2, 4, 2, 4, 2, 4, 2 until you get to the end. All the things are the same that we're used to. So n is the number of subintervals, x sub 0 is the beginning number, x sub n is the ending number, and then delta x is still found the same way. B minus a over n is the width of each subinterval. Okay, so let's just do one example together. We will approximate the integral of the natural log of x from 3 to 5, and we'll use that with n equals 4. Okay, so over here is the graph of the natural log, just a part of it, and we're approximating the area under the curve from 3 to 5, so that's all of this stuff here, and we're going to approximate the curve here with curves with parabolas, so second degree things. Okay, so first thing, we're going to want to find the width of each thing. So that's, again, it's just b minus a over n, not 3n. That's just when we put it together to approximate the area. So b is 5, a is 3, 5 minus 3 is 2, 2 over 4 is 1/2. Okay, then we want to find the values that we're going to plug in. So n is 4, so we're going to have go up to x sub 4. We start at 3 and we end at 5. And then it's going to go up by half each time. I'm just going to use decimals this time. You can use fractions if you want. So we'll go up by 0.5, so 3, 3.5, 4, 4.5, and then 5. All right, now Simpson's rule, we'll say s sub 4, and then it's b minus a over 3n, so that's 5 minus 3 over 3 times 4. Okay, alternatively, you can take your b minus a over n, what we found, and just put multiply by a 3 in the denominator, or divide it by 3. And then we're going to do, so it's f of the first thing, f of x sub 0. Okay, then we add, and then the first one that comes, so the second one, the first one that comes out of the first one starts with a 4 multiplied. So this will be 4 natural log of the natural log of 3.5. Okay, then we switch to a 2. Then we switch back to a 4. And then we're at the last one, so that one doesn't have any number multiplied. So that's just plus 1 times natural log of 5. So again, just to reiterate, we've got the ends, just have 1 in the front, then we have 4, 2, 4, and the middle ones will alternate like that, starting and ending with 4, and then 2's in the middle. And so if you calculate each of these separately, again, like don't round too much. If you have a graphic calculator, maybe hold it for as many places as it will, and then add them up. But anyway, here's each one individually with the numbers multiplied in, like the 4's and the 2's. And if you add this up and you divide by 6, you should get approximately 0.6262. So there's the approximate area under that curve using Simpson's rule. So that's it for this section. It's just those two things. Again, just things to pay attention to with the formulas, like the denominator in the beginning, you've either got 2n or 3n for trapezoid and Simpson's rule, and then we have these numbers in the middle. For trapezoid, they're all 2's for the middle things, and for Simpson's rule, we've got to alternate 4, 2, 4, 2, starting with the 4. So I hope this makes sense. Go ahead, like I said, and try it on Web Design, see how it goes. If you have any questions, please let me know.